In this video, I'm going to demonstrate how you can measure very precise time intervals using the SEELab or ExpEYES device. So we have these digital inputs into and sen, where sen also has analog measurement properties. And I've connected a wire from the square wave output, which we'll use as a test signal for this demo, and connected it to sen. I've also connected square wave to an LED, which goes to ground. And this particular LED will allow you to visualize at least the low frequency signals. So let me just map A1 to sen. So the sen input voltage is being seen here. Now let me apply some frequency to SQ1. Let's say 3 Hertz or say 5 Hertz. So at 5 Hertz, you can see the trace jumping up and down. So let me increase the time base a little bit. There you go. So now you can see that there is a signal on the screen. And now if I ask you, what is the time period of this? Let me freeze it. So the normal way to go about is, where does the waveform start? So around 173 milliseconds, the wave starts. And one full waveform ends here, which is about 373 milliseconds. So that gives you 200 milliseconds of time period. So frequency is 1 by 0.2, which gives you the 5 Hertz that we applied here. Now this is not very feasible for higher frequency signals because this is an oscilloscope and it's just measuring per unit time. So every voltage, at best, you can get 1 voltage at every 1 microsecond. So if you want to do like faster, more precise measurements where we're only concerned with the start signal and the stop signal, we need to use, under the mechanics submenu, you will find the digital stopwatch. Now, there's a photo here of one particular example where we're measuring the velocity of an object, how much time it takes to go around a track. So I have a photo transistor here where the emitter is connected to ground and the collector is connected to sen. Now, sen is internally pulled up using a 5K resistor, so its voltage is at 3.3 volts. And whenever the photo transistor conducts, which is when light falls on it, the sen signal will go low. So because of this LED, the signal is always low. But when an object gets in the path, the signal goes high momentarily, which is called a rising edge. From low to high is rising edge, and from high to low is called a falling edge. So right now I have the square wave connected to sen. Let me give some sort of frequency here, 10 Hertz, which you can see flickering at 50% duty cycle. Now, the signal that I want to measure is rise to rise time. Input 1 is sen, input 2 is also sen. So the stopwatch is started when there is a rising edge on sen. So sen has to be low initially, goes high, stopwatch is started. Then it will come back low. The second time that it goes high, the stopwatch is stopped. Let me click on measure. 100 milliseconds is the time period, which is correct for a 10 Hertz signal. Let me give a 1000 Hertz signal. 1 millisecond is the time period, right? So go back to 10, 100 milliseconds. So this is rise to rise time. Now, if I make this 10% duty cycle, the LED is on 10% of the time, off 90% of the time, but the total time period still remains 100 milliseconds. But if you take rise to fall time and measure that, you get only 10 milliseconds because it's a 10% duty cycle. And if I take fall to rise time, you get 90%, which is 90 milliseconds. So you have this very precise measurement setup where you can have different inputs as well. You can have the start signal on sen and the stop signal on into. That really depends on the applications that we can design with this. One of them is the measurement of gravity using time of flight. So you drop an object, and for that you have to use one of the set to rise time or clear to rise time or clear to fall time options. So let's say I want clear to rise time. So what this does is it will clear this digital output, which means initially OD1 is on, right? And clear means it will set it low. So if we have an electromagnet connected to OD1 and a little object stuck to the electromagnet, the moment you click on measure, it will first turn off the electromagnet by setting OD1 low and start stopwatch. And when does it stop? When sen has a rising edge signal on it. So that's how your clear to rise time signal works. So for the time of flight setup, we actually have the clear to fall time, where OD1 is set low to turn off the electromagnet, and SEN is high because the plates at the bottom are not touching. The moment the object hits the plates, it shorts to ground and gives you a low signal. So using these, we can measure different types of time signals. Now there is also a little plot here. So if I set this to 1000 Hertz, 10%, and click on repeat and say measure. So this is actually measuring, and okay, so I'm using clear to fall, so that's why the junk values are there. Let me use rise to rise time and say measure again. Yeah, so I'm getting precisely 0.001 and that's not changing. Now let me try rise to fall time, which is actually the duty cycle thing, 10%. Let me start measuring again. Now if I increase duty cycle to 20%, 30%. So you get the idea. You have a plot where you can continuously measure time intervals. This can be used as a lap timer or whatever physics experiments. We're going to come up with a few more experiments using this particular digital stopwatch. Right. Thank you for listening.